Today, under statistical thermodynamics, we will be looking at a Maxwell Boltzman distribution law. Now, this Maxwell Boltzman distribution law, it was given before the advancement of quantum mechanics, and hence it is known as classical statistics. And now, over here, we will be discussing only the important points. Detailed derivation is in the pin comment. We are considering that particles are distinguishable and they are identical, and there is no restriction in occupancy of the energy level. That is, any number of particles can occupy any energy level, and the particles that obeys Maxwell-Boltzmann distribution law, they are known as either Boltzmannians or they are known as Maxwellians. So suppose if we are considering that we have any system having n number of particles and the total energy of the system is ET. So suppose we can take any gas, say hydrogen gas, oxygen gas, nitrogen gas, or any xyz, any particular system, and over here we are considering that suppose we have n0 number of particles in energy level E0, n1 number of particles in energy level E1, and up to ni number of particles in energy level EI, and we are initially we are considering that the system is non-degenerate system. So for such a distribution, the thermodynamic probability is written as W is equal to n factorial upon capital pi of ni factorial. Now when we simplify this expression, we will get this particular expression, that is summation ln ni dni is equal to 0, and this is the most probable distribution. This is the expression for most probable distribution. We will have ln of w will be equal to 0 because W is the thermodynamic probability, and under equilibrium condition the value of thermodynamic probability is maximum. This you can see from this example also. You can see that in this particular distribution the value of thermodynamic probability is maximum. So the particles will have choice to sit in any of the three, but under equilibrium condition they will sit under this particular configuration only, and this will have this macro state will have maximum number of micro states, and under equilibrium or under most probable distribution, the system will assume the configuration in which it has maximum number of micro states as compared to the other, and hence this is a unique and this is a single valued so hence dl and w will be equal to 0, and when we simplify it we will get this particular expression, that is the most probable distribution. Now further, when we will apply Lagrange's method of undetermined multiplier, as we need to bind this between the number of particles and energy, and further when we solve this expression, the final expression that we will be obtaining is this, that is ni is equal to e raised to minus alpha into e raised to minus beta ei, where alpha and beta are constants and the value of beta is 1 upon kt, where k is the Boltzmann constant. We can write it as kb also. K is the Boltzmann constant and T is the absolute temperature. So this particular expression is known as Boltzmann distribution law, and basically this gives the distribution of particle between different energy level. Now we could take summation of this. So when we take summation, we know that summation of ni are equal to the total number of particles, and that we could write it as alpha is constant, so it will come out, and we could write it this way. So now we could take the ratio of both this, that is ni upon n is equal to e raised to minus alpha in the numerator, and in the denominator will be cancelled out, and we will have e raised to minus beta ei upon summation e raised to minus beta ei, and this particular expression is the Maxwell-Boltzmann distribution law. This expression, it gives the relative distribution of particles in different energy levels, that is how a total number of particles are distributed amongst different energy levels. So this is the expression when we are considering the system is non-degenerate one. When we are considering degeneracy, we need to introduce statistical weight factor gi. So when I introduce statistical weight factor in the numerator as well as in the denominator, then this will be the expression for the Maxwell-Boltzmann distribution law for degenerate system. Hope the very quick explanation is clear. Thank you very much.